All right, where were we? We made a bit of a mess, kind of working out this function. We figured out that this has two sides, one with a 1 minus t and the other side with a t minus 1 version, depending on which side we're on here. On the left-hand side, we have the t minus 1 version, and on the right-hand side, we have the 1 minus t version. And what we need to do then is kind of think through the steps one more time, hopefully just one more time, goodness. Okay, so over here, the light cone, whoops. The light cone is generated from x comma t equals t minus 1 comma t, where t is in 0.5 to 1. Over here, x comma t is generated from coordinates t1 minus t comma t, where t is a member of 0.5 comma 1. Okay, and then from there we can find, because this is a mapping of tau versus phi, tau coming this way, phi going that way. So tau is arctanh of x over t. Nope, this is phi. Phi is arctanh of x over t. Tau is square root of t squared minus x squared. So on the left-hand side, this is arctangent of t minus 1 over t over square root of t minus 1 squared minus x squared. I'm sorry, t minus 1 minus t squared, sorry, t squared minus x squared is d squared minus d minus 1 squared. That's what that is. Okay, so this would be if phi is less than 0, then phi equals arc, let's see, phi of cone is arctangent of t minus 1 over t. So that means tangent of the phi of the cone is going to be t minus 1 over t. Then we'll multiply by t, and then we'll subtract t, and then we'll divide by hyperbolic tangent of the phi of the cone minus 1. Now, we want a t minus 1. I'm not sure if there's any huge value doing this, but let's find out what t minus 1 is, if there's a simplification we could make here. Actually, there is, because the minus 1 minus tanh phi sub c plus 1 will cancel out, and we'll just have hyperbolic tangent of phi sub c divided by hyperbolic tangent of phi sub c minus 1. So that means our tau, which was t squared minus t minus 1 squared, square root of t squared minus t minus 1 squared, is going to be negative 1 over tangent phi minus 1 squared minus tangent phi over tangent phi minus 1 squared square root. But I don't really need to know that, because most of this can be done by Mathematica. I just know that the tau of the cone on the left is going to be equal to this value. On the right, things are going to be pretty similar. We're going to have arctangent of 1 minus t over t over square root of t squared minus 1 minus t squared. And we'll say this is if phi greater than 0. Actually, I don't know what I'm dividing here. There was no division here. These are just two separate equals statements. The rapidity is hyperbolic arctangent of x over t, which is hyperbolic arctangent of t minus 1 over t on the left, and on the right it's this, and this is on the left taucone on the left, and this is taucone on the right. So if phi is greater than 0, then phi of the cone is hyperbolic arctangent of 1 minus t over t. We want to solve that for t. Can skip maybe a couple steps here. Can at least skip down to this step. We'll have t of the cone times tanh of phi of the cone equaling 1 minus t. We'll add t to both sides. So we'll have t cone times tangent phi c plus 1 equals 1. So the time in the cone is 1 over 1 plus hyperbolic tangent of phi sub c. And then I'm not going to bother calculating t minus 1, but I'm going to let mathematica take care of that. But we'll have tau of the cone will be square root of t of the cone minus 1 minus t of the cone squared. So this is on the right. So given the value of phi, any value of phi, we can call that phi sub c. We can calculate t sub c of phi sub c, and then from that we can calculate tau sub c from t sub c of phi sub c. So all we've done so far is, given this point, figure out what this point is. That's all we've done so far. We figured that out. From this, we figure out t sub c, and then we figure out tau sub c. That's all we've done. And now what we need to do is take this thing, which is this distance here, which is 1 minus tau sub c, and we're going to take 1 minus tau sub c, and we're going to create a ratio with phi sub c, and the ratio is going to be phi sub c over 1 minus tau sub c is going to be greater than 1, I think, because this is curved outward. So this value here is always going to be a little bit longer than this value here. All right, the other thing we need to think about is the point that we're looking at. We'll call this, say, point here, we'll call that point phi sub p comma tau sub p. It's the point that we want to stretch. And what we're going to do with that point, it's going to be the input to the algorithm, the point that we're transforming. And what we're going to do is we're going to leave tau sub p alone, of course. Or we're going to leave phi sub p alone here because we want it to stay the same coordinate as the cone. But we're going to take 1 minus tau sub p, 1 minus tau sub p, and we're going to take 1 minus tau sub p and multiply it by this scaling factor here, v sub c over 1 minus tau sub c, to stretch it out. And then we've got a choice. We can either do nothing more with this, in which case this number, all this level 1 here, would be mapped to 0, because 1 minus 1 would be 0. Or if we want to leave this line at the same place, we could add 1. So that what is 1 on this chart would be 1 on the conformal mapping chart. If we did that, then these would not stop at 0. They would continue on down basically to infinity, I think. Maybe not at this point wouldn't be infinity, but this point would map to infinity. So now it's time to start coding in Mathematica, I think. I think I've got it pretty well thought out. We're going to make it into a module with a few extra variables, such as phi c, which is the rapidity of the cone, or to be more explicit, it's the rapidity of the Hubble observer who is observed by that cone, or is in the light, or produces the light that creates that cone, right? So we've got phicone and taucone. Of course, phicone is just equal to phi. I'm also going to put in tcone, which is, if phi is less than 0, then we'll have -1 over tanh phi minus 1. And then if not, it's going to be, what was our other version? 1 over 1 over 1 plus tanh of c phi. Okay, and then what's next? Next is taucone, which is if phi is less than 0, then we're going to have square root of tcone squared minus, minus tcone minus 1 squared. Okay, why is this one coming up that way and that one is coming up different? Don't know. Okay, so taucone is another conditional. If phi is less than 1, it's t minus 1 squared, t squared minus t minus 1 squared. If phi is greater than 0, we're going to have t minus 1 minus t squared. Then we're going to have the stretch factor. So I'll add that here. Stretch. It's not going to be y. It's going to be escape cu, which almost looks like a y. Stretch y. And their stretching of the conformal time, and that's what that variable is supposed to represent, is going to be escape c phi cone divided by 1 minus tau cone. And hopefully, and then we'll actually set our conformal time to be 1 minus tau Tau is the original tau. I don't think I've used it yet. Yeah, it's this tau right here. That's the tau of the actual point we're working with, and I have not. This is the first time I've used it in the code in the function. And we're going to multiply that tau by 1 minus tau times escape c cone divided by 1 minus tau cone. And actually, this needs to be negative. This is going to have to be a negative number because it's going to be something less than 1. And I could choose to add 1 here or not. Just for the heck of it, I'm going to add 1 just so that the number at the top stays 1. I'm not sure if that's necessary or not. And then we're going to return the value escape c escape c comma escape c capital U escape and semicolon. Looks like I don't have conformaltau in there, comma, so I need to add that to my list of variables in the module. Escape CU. Okay, that's our conform function. Takes in phi comma tau and returns phi comma conformaltau. Now, can I use this function now? I know that I can't because all of the points below here are going to go to infinity. This is actually the only point that is going to go to infinity, but I need to figure out what to do with those points so that they don't cause a ruckus. Out of sight, out of mind. All right, we'll set the graphics so that they're going to cover a region, like a non-infinite region, of course. So if I take all of the points of the form 0, 0, and simply map them down to, say, I don't know, conformaltau negative 1000, and then they'll just be not in the graph, and I won't have to worry about them. So I'm going to put a if statement here, asking if c comma tau equals 0, 0, then return negative 1000, 0. Else, we go through all of this and return that. Boom. End of if statement. Actually, we want this the other way around. 0, negative 1000. Okay. Okay, on running it, I find I have some issues. We've got quite a few more indeterminates than I was expecting, but that's okay. Where'd they come from? So what does it look like it happened to the points? It does appear that our Hubble observers are sort of represented. The black lines are the Hubble observers. It does seem to have those cone shapes, but it's moved them into some strange places. And it also seems to have these, what are these? These were the Euclidean coordinates. I forget, green was the spatial Euclidean coordinates. And it does look like these are actually hitting right here and then dropping all the way down to that 0, -1000 point that I scheduled. So that looks like where those almost nearly vertical lines are going, probably down to that point. The light cone points seem to have failed completely. So I'm going to have to figure out why that completely failed. And also the red the Euclidean lines of simultaneity are gone. So I'm going to have to figure out where those went. All right, but it's a start. So thanks for watching.